Whoa. What up, what up? It's me again. It's been raining like crazy, torrential downpour here in Northern California, but it's let up a little bit. Haven't seen any trucks in a while, so we're just going to go for it. See how far we can make it. Continuing the reading of Robert M. Sapolsky's Behave in Chapter 2, page 32. Not entirely sure where I left off, but it's somewhere right here. Okay. And what does the amygdala damage do to aggressive behavior? This was studied in humans where amygdalotomies were done to control seizures, not to control seizures, but to control aggression. Such psychosurgery provoked fiery controversy in the 1970s. And I don't mean scientists not saying hello to each other at conferences. I mean a major public shitstorm. Well, shit. I was gonna say those guys are really impatient because I just heard him pull up and he honked the horn, but looks like I just let the last one out, hopefully. Okay. The issue raised bioethical lightning rods. What counted as pathological aggression? Who decided? What other interventions had been tried unsuccessfully? Were some types of hyperaggressive individuals more likely to go under the knife than others? What constituted a cure? Most of these cases concerned rare epileptics where seizure onset was associated with uncontrollable aggression, and where the goal was to contain that behavior. These papers had titles such as Clinical and Physiological Effects of Stereotaxic Bilateral Amygdalotomy for Intractable Aggression. The fecal hurricane concerned the involuntary lopping out of the amygdala in people without epilepsy, but with a history of severe aggression. While doing this could be profoundly helpful or Orwellian, this is a long, dark story, and I will save it for another time. Did destruction of the human amygdala lessen aggression? Pretty clearly so. When violence was a reflexive, inchoate outburst preceding a seizure. But with surgery done solely to control behavior, the answer is, maybe. The heterogeneity of patients with surgical approaches, the lack of modern neuroimaging to pinpoint exactly which parts of the amygdala were destroyed in each individual, and the imprecision in behavioral data, with papers reporting from 33 to 100% success rates, make things inconclusive. The procedure has almost entirely fallen out of practice. The amygdala aggression link pops up in two notorious cases of violence. The first concerns Ulrich Meinhof, a founder in 1968 of the Red Army faction. aka the Baader-Meinhof Gang, a terrorist group responsible for bombings and bank robberies in West Germany. Meinhof had a conventional earlier life as a journalist before becoming violently radicalized. During her 1976 murder trial, she was found hanged in her jail cell. Suicide or murder? Still unclear. In 1962, Meinhof had had a benign brain tumor surgically removed. The 1976 autopsy showed that remnants of the tumor and surgical scar tissue impinged on her amygdala. The second case concerns Charles Whitman, the 1966 Texas Tower sniper, who, after killing his wife and mother, opened fire atop a tower at the University of Texas in Austin, killing 16 and wounding 32, one of the first school massacres. Whitman was literally an Eagle Scout and childhood choir boy, a happily married engineering major with an IQ in the 99th percentile. In the prior year, he had seen doctors complaining of severe headaches and violent impulses, e.g., to shoot people from the campus tower. He left notes by the bodies of his wife and his mother proclaiming love and puzzlement at his actions. I cannot rationalize or pinpoint any specific reasoning for killing her, and let there be no doubt in your mind that I love this woman with all my heart. His suicide note requested an autopsy of his brain, and that any money he had be given to a mental health foundation. The autopsy proved his intuition correct. Whitman had a glioblastoma tumor pressing on his amygdala. Did Whitman's tumor cause his violence? Probably not in a strict amygdaloid tumor equals murderer sense, as he had risk factors that interacted with his neurological issues. Whitman grew up being beaten by his father and watching his mother and siblings experience the same. This choir boy Eagle Scout had repeatedly physically abused his wife and had been court-martialed as a Marine for physically threatening another soldier. Wait, don't the Marines want you to be physically threatening? Don't they train you to be that way? This is a great example of the big theme of this book, namely the context dependency of our best and worst behaviors. What the Marines train people for is to be majorly physically threatening, in certain contexts only. And perhaps indicative of a thread running through the family, his brother was murdered at age 24 during a bar fight. A whole other domain of amygdaloid function to the center stage. Thus, considerable evidence implicates the amygdala in aggression. But if you asked amygdala experts what behavior their favorite brain structure brings to mind, aggression wouldn't top their list. It would be fear and anxiety. Crucially, the brain region most involved in feeling afraid and anxious is most involved in generating aggression. The amygdala-fear link is based on evidence similar to that supporting the amygdala aggression link. In lab animals, this has involved lesioning the structure, detecting activity in its neurons with recording electrodes, electrically stimulating it, or manipulating genes in it. All suggest a key role for the amygdala in perceiving fear-provoking stimuli and in expressing fear. Moreover, fear activates the amygdala in humans, with more activation predicting more behavioral signs of fear. In one study, objects in a brain scanner played a Miss Pac-Man from Hell video game, where they were pursued in a maze by a dot. If caught, they'd be shocked. When people were evading the dot, the amygdala was silent. However, its activity increased as the dot approached. The stronger the shocks, the farther away the dot would be when first activating the amygdala. The stronger the activation, and the larger the self-reported feeling of panic. In another study, subjects waited an unknown length of time to receive a shock. This lack of predictability and control was so aversive that many chose to receive a stronger shock immediately. And in the others, the period of anticipatory dread increasingly activated the amygdala. Thus, the human amygdala preferentially responds to fear-evoking stimuli, even stimuli so fleeting as to be below conscious detection. Powerful support for an amygdaloid role in fear processing comes from post-traumatic stress disorder, PTSD. In PTSD sufferers, the amygdala is overreactive to mildly fearful stimuli and is slow in calming down after being activated. Moreover, the amygdala expands in size with long-term PTSD. This role of stress in this expansion will be covered in Chapter 4. The amygdala is also involved in the expression of anxiety. Take a deck of cards. Half are black, half are red. How much would you wager that the top card is red? That's about risk. Here's a deck of cards. At least one is black, at least one is red. How much would you wager that the top card is red? That's about ambiguity. The circumstances carry identical probabilities, but people are made more anxious by the second scenario and activate the amygdala more. The amygdala is particularly sensitive to unsettling circumstances that are social. A high-ranking male rhesus monkey is in a sexual consortship with a female. In one condition, the female is placed in another room where the male can see her. In the second, she is in the other room along with a rival of the male. No surprise, that situation activates the amygdala. Is that about aggression or anxiety? Seemingly the latter. The extent of activation did not correlate with the amount of aggressive behaviors and vocalizations the male made or the amount of testosterone secreted. Instead, it correlated with the extent of anxiety displayed, e.g., teeth chattering or self-scratching. The amygdala is linked to social uncertainty in other ways. In one neuroimaging study, a subject would participate in a competitive game against a group of other players. Outcomes were rigged so that the subject would wind up in the middle of the rankings. Experimenters then manipulated the game outcomes so that subjects' rankings either remained stable or fluctuated wildly. Stable rankings activated parts of the frontal cortex that we'll soon consider. Instability activated the frontal cortex plus the amygdala. Being unsure of your place is unsettling. Another study explored the neurobiology of conforming. To simplify, the subject is part of a group where secretly the rest are Confederates. They are shown X, then asked, "What did you see?" Everyone else says Y. Does the subject lie and say Y also? Often. Subjects who stuck to their guns with X showed amygdala activation. Finally, activating specific circuits within the amygdala in mice turns anxiety on and off. Activating others made mice unable to distinguish between safe and anxiety-producing settings. By the way, what does mouse anxiety look like? Mice dislike bright lights and open spaces. Go figure, for a nocturnal animal that lots of species like to eat. So one measure of mouse anxiety is how long it takes for a mouse to go into the center of a brightly lit area to get some food. The amygdala also helps mediate both innate and learned fear. The core of innate fear, aka a phobia, is that you don't have to learn by trial and error that something is aversive. For example, a rat born in a lab, who has interacted only with other rats and grad students, instinctually fears and avoids the smell of cats, while different phobias activate somewhat different brain circuitry. For example, dentist phobia involves the cortex more than does snake phobia. They all activate the amygdala. Such innate fear contrasts with things we learn to fear: a bad neighborhood, a letter from the IRS. The dichotomy between innate and learned fear is actually a bit fuzzy. Everyone knows that humans are innately afraid of snakes and spiders, but some people keep them as pets and give them cute names. We even have that profound renunciation of arachnophobia, namely kids becoming bereft when Charlotte dies in Charlotte's Web. Instead of inevitable fear, we show prepared learning, learning to be afraid of snakes and spiders more readily than of pandas or beagles. The same occurs in other primates. For example, lab monkeys who have never encountered snakes or artificial flowers can be conditioned to fear the former more readily than the latter. As we'll see in the next chapter, humans show prepared learning, being predisposed to be conditioned to fear people with a certain type of appearance. The fuzzy distinction between innate and learned fear maps nicely onto the amygdala structure. The evolutionarily ancient central amygdala plays a key role in innate fears. Surrounding it is the basolateral amygdala, or BLA, which is more recently evolved and somewhat resembles the fancy modern cortex. It's the BLA that learns fear and then sends the news to the central amygdala. Joseph Ledoux at New York University has shown how the BLA learns fear. As an important point through this book, whenever I describe work done by Jane Doe or Joe Smith, I actually mean work done by Doe and a team of her post-Does, technicians, grad students, and collaborators spread far and wide over the years. I'll be referring solely to Doe or Smith for brevity, not to imply that they did all the work on their own. Science is utterly a team process. In addition, as long as we're at it, another point. At endless junctures throughout the book, I'll be reporting the results of a study along the lines of, and when you do whatever to this or that brain region, neurotransmitter, hormone, gene, etc., X happens. What I mean is that on the average, X happens, and at a statistically reliable rate. There is always lots of variability, including individuals in whom nothing happens, or even the opposite of X occurs. Expose a rat to an innate trigger of fear, a shock. When this unconditioned stimulus occurs, the central amygdala activates. Stress hormones are secreted. The sympathetic nervous system mobilizes, and as a clear endpoint, the rat freezes in place. What was that? What do I do? Now do some conditioning. Before each shock, expose the rat to a stimulus that normally does not evoke fear, such as a tone. And with repeated coupling of the tone, the conditioned stimulus, with the shock, the unconditioned one, fear conditioning occurs. The sound of the tone alone elicits freezing, stress hormone release, and so on. This is termed Pavlovian conditioning, in a nod to Ivan Pavlov. It's the same process by which Pavlov's dogs learn to associate the conditioned stimulus of a bell with the unconditioned stimulus of food, so that the former eventually was able to provoke salivation. Less reliable are operant conditioning approaches, in which the degree to which something is scary is assessed by how much an individual will work to avoid being exposed to it. Ledoux and others have shown how auditory information about the tone stimulates BLA neurons. At first, activation of those neurons is irrelevant to the central amygdala, whose neurons are destined to activate following the shock. But with repeated coupling of tone with shock, there is remapping, and those BLA neurons acquire the means to activate the central amygdala. As usual in science, things aren't all that clean. Some of those plastic changes during fear conditioning also occur in the central amygdala. Hey Mikey, good to see you. Just doing a little reading here. Late night. BLA neurons that respond to the tone only once conditioning has occurred would also have responded if conditioning instead had been to a light. In other words, these neurons respond to the meaning of the stimulus rather than to its specific modality. Moreover, if you electrically stimulate them, rats are easier to fear condition. You've lowered the threshold for this association to be made, and if you electrically stimulate the auditory sensory input at the same time as shocks, i.e. there's no tone, just activation of the pathway that normally carries news of the tone to the amygdala, you cause fear conditioning to a tone. You've engineered the learning of a false fear. There are synaptic changes as well. Once conditioning to a tone has occurred, the synapses coupling the BLA and central nucleus neurons have become more excitable. How this occurs is understood at the level of changes in the amount of receptors for excitatory neurotransmitters in dendritic spines in these circuits. Just to make things more complicated, the BLA neurons are probably talking to the central amygdala neurons via middlemen called intercalated cells. Furthermore, conditioning increases levels of growth factors, which prompt the growth of new connections between BLA and central amygdala neurons. Some of the genes involved have even been identified. We've now got learning to be afraid under our belts. I would be remiss not to touch on one issue in this field. When a new fear is learned, where is that memory stored? Next to the amygdala is the hippocampus, which plays a role in explicit learning about straightforward facts, e.g. someone's name, while the hippocampus is where short-term knowledge about the name is turned into long-term memory. The memory trace itself is most likely in the cortex. The hippocampus, to use a metaphor that will probably be obsolete by the time this book sees the light of day, is the keyboard, the conduit, the portal to the cortical hard drive where a memory is stored. Is the amygdala solely the keyboard, with fear memories stored elsewhere, or is it the hard drive as well? This has been an ongoing, unresolved debate in the field, with the keyboard plus hard drive, view championed by Ledoux at the keyboard, and the keyboard alone view espoused by the equally accomplished scientist James McGaugh of the University of California at Irvine. Now conditions change. The tone still occurs now and then, but no more shock. Gradually, the conditioned fear response abates. Getting pretty good at this game. How does fear extinction occur? How do we learn that this person wasn't so scary after all? There's another one. I wonder if they're all going to come back now. Oh yes, I enjoy this book greatly. Second time reading it? It's like we're clear now. Different doesn't necessarily equal frightening. Recall how a subset of BLA neurons respond to the tone only once conditioning has occurred. Another population does the opposite. Um, Another population does the opposite, responding to the tone once it's no longer signaling shock. Logically, the two populations of neurons inhibit each other. Where do these, oh, the tone isn't scary anymore, neurons get inputs from? The frontal cortex. When we stop fearing something, it isn't because some amygdaloid neurons have lost their excitability. We don't passively forget that something is scary. We actively learn that it isn't anymore. An example of the sort of complexity we're up against here. Both fear conditioning and fear extinction involve activation of inhibitory neurons. That commonality seems weird, given opposite outcomes. It turns out that the extinction involves activation of neurons that inhibit excitatory neurons, while fear conditioning involves activation of inhibitory neurons that inhibit other inhibitory neurons that project onto excitatory neurons. a double negative equaling a positive. The amygdala also plays a logical role in social and emotional decision making. They all went out at once, they're all coming back in at the same time. Okay, finish this page. In the ultimatum game, an economic game involving two players, the first makes an offer as to how to divide a pot of money, which the other player either accepts or rejects. If the latter, neither gets anything. Research shows that rejecting an offer is an emotional decision, triggered by an anger at a lousy offer and the desire to punish. The more the amygdala activation in the second player after an offer, the more likely the rejection. People with damaged amygdalae are atypically generous in the ultimatum game and don't increase rejection rates if they start receiving unfair offers. Seems like each time I sit down now, another truck comes in. There were 6 that went out first started this. Let's see how many pages we have left to go in this chapter. I know this is a lengthy one. Yeah, Sapolsky is quite brilliant. He's a primatologist and a neurobiologist, I think. Let's see, he described it in the beginning. That's interdisciplinary. Oh, here's another chart. Yeah, I thought I was going to get a bit of downtime because of the rain here, but they're trying to keep me on my toes, see. Got still quite a bit left to go in this chapter. See if I can get through just this section. And then, oh yeah. Got about 40 pages left to go in this chapter, actually. So we'll save it for a part 3. Let's see if I can just finish this section here up real quick. Okay. These individuals understand the rules and can give sound strategic advice to other players. Moreover, they use the game strategies as control subjects in a non-social version of the game, when believing the other player is a computer. And they don't have a particularly long view undistracted by the amygdala's emotional tumult, reasoning that their non-contingent generosity will induce reciprocity and pay off in the long run. When asked, they anticipate the same levels of reciprocity as do controls. Instead, these findings suggest that the amygdala injects implicit distrust and vigilance into social decision-making, all thanks to learning. In the words of the author's study, the generosity and the trust game of our BLA-damaged subjects might be considered pathological altruism, in the sense that inborn altruistic behaviors have not, due to BLA damage, been unlearned through negative social experience. In other words, the default state is to trust, and what the amygdala does is learn vigilance and distrust. Unexpectedly, the amygdala and one of its hypothalamic targets also play a role in male sexual motivation. Other hypothalamic nuclei are central to male sexual performance. How might you distinguish between sexual motivation and performance in a male rat? Well, the latter is easy. What's the guy's frequency and latency when with a sexually receptive female? But sexual motivation? This is measured by determining how often a male will press a lever in order to get access to a female. But not females. I can't resist mentioning a case report of a woman with epileptic seizures initiating in the amygdala. Before seizure onset, she would have the delusion that she was male, including a sense that she had a deep voice and hairy arms. Coffee. It is. It's all rainy out here. Oh, there's another truck. These boys are staying busy. All right. One neuroimaging study shed some light. Young heterosexual men looked at pictures of attractive women versus as a control of attractive men. Passively observing the pictures activated the reward circuitry just alluded to. In contrast, working to see the pictures by repeatedly pressing a button also activated the amygdala. Similarly, other studies show that the amygdala is most responsive to positive stimuli when the value of the reward is shifting. Moreover, some BLA neurons that respond in that circumstance also respond when the severity of something aversive is shifting. These neurons are paying attention to change, independent of direction. For them, the amount of reward is changing and the amount of punishment is changing are the same. Studies like these clarify that the amygdala isn't about the pleasure of experiencing pleasure. It's about the uncertain, unsettled yearning for a potential pleasure. The anxiety and fear and anger that the reward may be smaller than anticipated, or may not even happen. It's about how many of our pleasures and our pursuits of them contain a corrosive vein of disease. In contrast to this picture of growing, precarious arousal, the amygdala deactivates in both men and women during orgasm. Tanya Z. Yes, this is Behave, the biology of humans at our best and worst. There's a um, interdisciplinary study of human behavior, and quite interesting. Yeah, so he's a neuroscientist and primatologist, and essentially this is about fear and aggression and where it comes from. Nice to see you. Yeah, unfortunately, I will have to pick this up at a later time. But I thank you, Tanya Z and Mikey Sue's for coming. Yeah, if you want to catch up, I started in the first chapter a couple videos ago. So you can go back there and check it out. And I will be finishing this up fairly shortly here. Want to avoid any further interruptions right now. So I will be back soon. Much love, everybody.